Thank you. So yeah, today I want to talk about a more analytic method that appears in my master research, which is used to approximate, it's a classical method to approximate exponential sum. So what is an exponential sum? Exponential sum is a sum of the following form, which is basically just an sum of unit vectors in the complex plane, where the angle is determined by this a function f, deterministic function f. An example is partial sums of the zeta function, which is giving us an idea of why we might care about this type of structure, but there's plenty of other examples. So if I keep going with these examples, this is the visualization of exponential sums. Not all of them might look like this. This one is very nice. It has its curlicues. So this one is 8,000 times log of x. As you can see, the trivial bound, which would be 1,000, this is sum over 1,000 terms, is way up because we get these nice points of cancellation. So we might ask ourselves, when do we get these points of cancellation? And this happens to be the case when the derivative is very close to an integer. It's very far from an integer. We get that two consecutive terms are going to be in opposite directions, and we get cancellation. And when the terms are very close to an integer, we don't get cancellation. We get these consecutive terms being basically on a straight line. Hopefully, that's the only thing that's straight on this talk. So this is the van der Corput method, a little bit more formally. Like, how do you get it? Well, you first apply Poisson summation formula, which would give you a shorter sum, which is important for what the result in my project. And the stationary phase to approximate these integrals that appear in the sum is basically the heuristic of what I mentioned before, where if you have control over multiple derivatives of the function f, you can say something about the value where it peaks, where this function peaks. So x sub nu here being exactly where you have these integers. So yeah, this is one of the statements or one way of stating this method, where the important part again is having a shorter sum, and if we have nice bounds for the derivative, we also have a nice error term. So for my research, I'm just applying it to a particular Hardy-Littlewood polynomial, where we added an extra gamma, which can be any real number. And yeah, this is a little bit more probabilistic. What is the we're trying to find the limiting distribution of these polynomials, which a simulation might give us the intuition that it might be quite nice. So the key ingredient again is the van der Corput method. We apply it to shorten the sum, and we get also a nice expression where we get a real term and a phase function. So we are hoping that n is going to be for sufficiently large n. These two terms are going to become independent, or at least that's the intuition that we're getting. And to prove it, we apply the method of moments, compute the joint moments, and we obtain exactly as our intuition suggested, that this P sub n, the Hardy-Littlewood polynomials, are indeed have a limiting distribution that is a random variable h, which looks like this, u uniformly distributed, and depends on this gamma that we chose, and the omega j's, which are IID uniformly distributed around the unit circle. So you might notice that we have an extra assumption here. We need that e to the minus 1 gamma for simplicity, but also it is essential here. We need it to be transcendental because this is due to the fact that when we are computing the joint moments, we do get this nice real part, but the phase has this sum, and we can only guarantee, or we can guarantee that this sum is going to be 0 if and only if aj is equal to bj, only when e to the minus 1 gamma is transcendental, or at least it's easier. So that also begs the question of, what happens when e to the minus 1 gamma is rational, or what happens when it's algebraic? I haven't really thought about those questions yet, but this is a nice visual, another simulation of what might happen, or what happens at least with 10,000 entries of e to the minus 1 gamma equal to 2. And yeah, I believe this is everything I wanted to say. So thank you.